Welcome to all. We continue with random variable. Now, characteristic of random variable: mean value. We already this topic discussed with maths. Fxi for discrete case drv. If it is continuous, mu is come from expectation. Mu is also known as expectation. It's come from x fx dx. DC component. For communication point of view, this term is very useful. Second is mean square value. Square fx I equals to 1 to m for drv. For crv, I write this equation once again. Ex square for continuous x square fx dx. This is known as, this is in the CRV domain, total power, known as m2 also. Mean value is known as m1 also. Move to next page. Third, variance. Variance is represented by square m2 minus m1 square. Mean square value square mean value square of mean known as AC power, which is very useful in communication. Standard deviation, root of variance, sigma m2 minus m1 square. RMS value of AC component. RMS value. We jot down all the formulas, and now we discuss some gate question. A question in gate round 5. A density function is given to us. Density function given to us in this pattern. We can draw from 0 to 4 1 by 8 x by 8. Within 0 to 4 we want to calculate expectation, mean square, standard deviation and variance, all 4 parameters. First we calculate mean value. For mean value we consider integration from infinite to x. Just formula I write down, and by putting value in the formula x by 8 dx x cube upon 3 1 by 8 0 to 4. By putting value 1 by 8 64 by 3 8 by 3 is mean value mu. fx dx x by 8 first we write expression for x4 upon 4 1 by 8 value will be 0 to 4 4 16 into 16 divided by 8 into 4. Answer is 8 now. For variance, we can use this idea m2 this one m1 m2 minus m1 का whole square 8 by 3 minus just reverse the value 64 minus 64 divided by 9 64 oh I put wrong value 8 is the correct value 72 minus 64 upon 9 is 8 by 9. We can calculate in with formula also x minus 8 by 3 square x by 8 dx 0 to 4. By putting value we get 8 by 9. For standard deviation take a root of this 2 root 2 upon 3. We can calculate this. Some important property of mean is ek. If k is constant then expectation is same. K is mu plus k, both are same. A constant term is multiplied with random variable, mean is also multiplied with that. Added means shifting. And last case x and y. Expectation of these two is first and second one. We took an standard example, then calculate mean, variance, mean square, all the values. Standard probability density function, uniform PDF. First, uniform PDF. In the uniform PDF, I have a PDF of A to B in the range of A to B, height is B minus A. Fx is B minus A to B, otherwise 0. Then we can calculate mean value, mean mu equals to, by this formula, xfs dx. While applying formula we get the result x b minus a dx b minus a x square divided by 2 a to b square a square upon 2 b minus a. Then result will be b plus a divided by 2. Means mean value is in between a and b. Same in this same manner we can calculate x square fx dx minus infinite to infinite by putting value a to b x square dx b minus a. By solving this expression we get result x a square ab plus b square divided by 3. For variance m2 minus m1 square. By applying this we get variance is 12 square. And standard deviation is a minus b root of 2 root 3 is our answer. In this way we get all the answer. For uniform PDF, if now we took exponential density function and we want to calculate mean value, expectation, mean square, variance, standard deviation. Mean value function is defined as b power minus bx x greater than 0 less than 0 is 0. Then mean value is 1 by b, mean square is 2 by b square, variance is 1 by b square, standard deviation is 1 by b. By putting into the formula we can calculate this. Now we discuss the important function Gaussian density function, which is very useful in communication. Now we discuss Gaussian density function with next page. Gaussian density function, if Gaussian is PDF is Gaussian in nature, then function is defined in this way: 2 pi sigma square e power minus x minus mu whole square upon 2 sigma square, where mu is mean value and sigma is standard deviation. I can draw this. This is denote mu. Height of this function is 1 upon sigma 2 1 upon root 2 pi sigma square root of. I can draw this in this way. Example, in this pattern mu is m1 is mean value, second is mean square value, m2 is sigma square mu square, variance sigma square, standard deviation sigma. A numerical problem is jot down here 100. Then they ask us to find all the statistical parameter of this Gaussian pulse. Mu, by viewing mu we can say 2. Mean square value, this is m1, mean square value m2. M2 we can find out from this term, mu square sigma square, variance sigma square compare with 100, 2 sigma square is 100, sigma square is 50, sigma equals to root 2 5 root 2. Variance is 50 and mean square value is 50 plus 2 square means 54. Bilkul. And standard deviation is root of 50 is 5 root 2. In this way we calculate complete value of statistical parameter of Gaussian pulse. Now we calculate CDF of Gaussian pulse, which is very important for us. Gaussian pulse is very important for us. We want to calculate CDF of Gaussian PDF. PDF is Gaussian in nature for white noise. We want to calculate CDF of a Gaussian pulse. CDF of a Gaussian pulse via formula minus infinite to x fu du minus infinite to x 1 by 2 pi sigma square e power x minus mu whole square 2 sigma square dx. I took new variable because x and this limit is same. Fx x minus infinite constant come out e power minus zeta minus mu whole square 2 sigma square d zeta. Zeta minus mu upon sigma is z. D zeta upon sigma equals to dz. By putting this value and modify the limit, by putting infinite limit, no change. By putting x limit, large change. 1 upon root 2 pi. Sigma is used here instead of here. So dz and remaining terms are z square by 2 fxx. Now PDF is completely converted into CDF with new parameter where z is denoted by x minus mu upon sigma. This CDF and one more function is there which is known as complementary error function QZ complementary error function, which is defined in this way: from z to infinite e power minus z square by 2 dz. So we can write fx, because this limit is minus infinite to some level z, and z to infinite means both are combined together is equals to 1. So we can conclude in this way CDF can be calculated from this formula if complementary error function given to us. If CDF is given to us, we can calculate complementary error function. There is direct relation between these two. The Gaussian pulse is very important in this regard. We will revise some point regarding Gaussian. PDF of Gaussian can be represented in this way. CDF of Gaussian is marked as 1 upon root 2 minus infinite to x minus mu upon sigma naught square e power minus z square by 2 dz x equals to x minus mu upon sigma. QZ complementary error function is defined in this way: z up to infinite e power minus z square by 2 dz, a relation between fx CDF of Gaussian and 1 minus q x minus mu upon epsilon. And last relation between QZ half ERF C Z upon root 2 error coefficient function is equals to half 1 minus ERF x upon root 2. All the formula is revised. In short, ERFC x 2q x root 2 z, sorry. In this way we discuss the all type of formula. Now we will discuss a problem regarding Gaussian pulse. If x is random variable with Gaussian parameter is given to us, Gaussian pulse is defined n. N means Gaussian pulse. Mu and variance is denoted in this way, and Gaussian pulse want to change is standard normal random variable. X is changed into z, that is n 0 and 1. While change of by shifting and scaling, z is standard normal Gaussian pulse. Gaussian pulse is standard normal Gaussian pulse when mu equals to 0, mean value of Gaussian is 0 and standard deviation is 1. We can write expression for this from minus infinite to x minus mu upon sigma minus z square dz, where z and relation between z and x is given by. Now we want z of this, z x minus mu upon z less than z. So solve for x, z sigma plus mu. By putting this value, we get where a constant term is also there, 1 upon root 2 minus infinite to, instead of using x we use here z sigma plus mu minus mu upon sigma e power minus z square by 2 dz. Mu to cancel, sigma to sigma cancel. Final expression for us is 1 upon root 2 minus infinite to z e power minus z square divided by 2 dz. This expression I rewrite minus infinite to z minus 0 upon 1 dz. 0 denote mu value, 1 denotes sigma value. This represent a Gaussian pulse having mu equals to 0 and sigma equals to 1. If mu 0 means standard normalized standard Gaussian pulse. Now we take a A question from Gate 13 paper. U and V are two independent zero mean Gaussian random variable. Gaussian random variable with mu equals to 0 and variance are respectively 1 by 4 and 1 by 9. 1 by 4 and 1 by 9 respectively. The probability of 3v minus 3v greater than 2u is, we want to calculate this probability. P equals to 3v minus 2u is greater than 0. 3v minus 2u is z, is capital Z, new random variable, new Gaussian random variable. In this question, two random variable of Gaussian with zero mean are given to us, and those variance is given to us 1 by 4 and 1 by 9, and find the probability of this term. This term, by shifting this term is greater than 0, I assume a new parameter z, new Gaussian random variable z. 3v, what is 3v? V is a Gaussian pulse, variance is given to us 0 and 1. 0 is mean. If we multiply with a scaling component, mean is also scaled 3 into 0, and in the case of variance a square is multiplied, so 3 square 1 by 9 is 1. Now variance is revised variance is 1. 2u 0 1 and 2 into 0 4 2 square into 1 by 4 equals to 1. Again both are Gaussian pulse with normal standard Gaussian pulse. Both are normal standard Gaussian pulse. Now we want to subtract these two Gaussian pulse. By subtraction we get 0 to 2. How it is possible? N 3 0 2 into 0 plus 3 square 1 by 9 plus 2 square 1 by 4. It means new variance is 2, new mean is 0. It is not revised. 0 and variance is 2. And in this condition, this is a Gaussian pulse. A Gaussian pulse area greater than 0 is always half. If it is mean, Gaussian pulse is always symmetrical about mean. Symmetric means half of the area at right half of the mean and left half of the mean. Means direct answer is half. No other calculation is required for us. Directly we can say answer is half, because half of the area covered in right half of the mu and left half of the mu. This is the correct one. Next we discuss a discrete random variable question. X is a discrete random variable. Take value from 1 to 5 and probability are given to us. Different probability, 0.1, 0.2, 0.04, 0.2 and 1, 0.1. And we want to calculate the expectation of this. Expectation of this is come out from 1 to 5 xi I fxi. So we calculate the value x and fx value. By putting all the values we can get 1 multiply with 0.01, 2 multiply with 0.02, plus 3 multiply with 0.04, 4 multiply with 0.02, and 5 multiply with 0.01. By adding all the terms we get result is 3. For mean square value, same procedure, same formula is same, but some little difference. Squaring of this term means we have to square the this value, particular value. 1 square 0.1, 2 square 0.2, 3 square 0.4, plus 4 square 0.02, 5 square 0.01. By calculating all the terms we get 10.2. For variance purpose m2 minus m1 square, m2 is 10.2, m1 is 3 ka square, means 1.2 is our variance. That's all for random variable. Now start in new lecture we start digital communication.